In this section, we will discuss about another authentication scheme that is developed by Fiat Shamir. We say it Fiat Shamir. Okay. Before that, we will discuss about what is zero knowledge proof. Okay. So in a zero knowledge proof, the short term is JKP, where Alice want to prove to Bob that she knows the secret without revealing any information. Okay. So that neither Trudy or Bob can learn anything about the secret. So Bob must be able to verify that Alice knows the secret, okay. Even though he doesn't gain any information about the secret. Okay. So it looks sounds impossible. Like how can Alice can prove herself to Bob without revealing anything, right? But there is a interactive probabilistic process where Bob can verify Alice that she knows the secret. So there is a interactive proof system. Okay. So we'll discuss about that. So to describe about this protocol, we first consider this Bob's cave. Okay. So suppose Alice claims that she knows the secret phrase of like Kulja Sim Sim or Teaching Park or Open Sesame, something like that. Okay. So this is the secret phase. So Alice claims that she knows the secret phrase and that opened the door between R and S. Okay, so as you can see in the figure, there is a door between R and S. Okay, so to open the door, you have to say the magic word. So Alice need to prove that she knows the secret without revealing any information. So suppose Alice entered into the cave and she flips a coin, like which side she'll go, like in right side or the S side, this R side or in S side. Okay, so suppose in this case, like Alice is here. Okay. So Alice flip a coin and she think, okay, she will go to the slide R. Okay. So Alice came to this position R. Now Bob actually came in this position. So in Q position, Bob is here and Alice is here. So now Bob said to Alice that come out the S side. Okay, so that means now for Alice, if she know the secret message, she can open the door and came through the S side. Okay. But if Bob said that come to the right side, R side, then Alice will come in this way. Okay. So in that case, Alice doesn't need to open up the gate, right? But she can convince Bob that she knows the secret, but she doesn't know the secret. So there is a 50-50 chance. Okay. So without knowing the secret, Alice could come out from the correct side with the probability is half, 1 by 2. Right. So just think about this one. This only two case. If she knows the secret key, secret phrase, then only she can come through this door. So if Bob said come through side S and Alice come in this side, that means Alice doesn't know the secret phrase. But when Bob said come through our side, then Alice can come from this side without knowing the secret phrase. So if Bob repeat this thing in n time, so Alice can fool Bob with probability is 1 by 2 to the power n. Okay, so this is the Bob's cave. This is some kind of protocol, so now we will convert it to the to a protocol. So this protocol is called Fiat Shamir protocol. Okay, so in this protocol, uh, let's do it with without the cave. Okay, so in this protocol we consider that finding square root of module n is difficult. uh, we have seen earlier like factorization, okay, logarithm problem. Those problem are mp complete problems, so those are very difficult to break. So similarly, finding square root of modular n is somehow difficult. Okay, like we have seen like n equal to pq, where pq is prime number, so that is very difficult to find. Okay, so suppose Alice has a secret, or the secret message is s. Okay, so we compute n, so we know n, and we take the square of secret mod n, that is v. Okay, so here n and v, these are public value, public, and s is secret. Okay, just think about like this. So Alice, now the problem is Alice must convince Bob that she knows the S without revealing any information about S. Okay, so in a Fiat Shamir protocol, it's like Alice select a secret. Alice select a random value R, and suppose she knows the secret. So the secret is S. So she compute x equal to r square mod n and send it to Bob. Then Bob choose 0 or 1. Okay, so he can choose it randomly. Then Alice compute a r into s to the power e and send it to Bob. So r, she knows r, okay, and that is the secret. S, it is also known to Alice, and the e, that is Bob, is selected from here. Okay, so what Bob have to do? Bob have to verify this one. Okay, so if Bob can verify this one, if it is true, then we can say that Alice knows the secret, otherwise not. Okay, let's think about this part. Suppose there are two cases, as I said, that Bob can choose e equal to 1 or e equal to 0. Okay, so if Bob's select e equal to 1, so in the equation we will have r into s to the power 1. Okay, so these values are known value, so Bob chooses equal to 1. So if this is a valid equation, if that is true, then Bob accept that Alice knows the secret. Okay, so if Alice doesn't know the secret, she cannot verify herself to Bob. So if I just summarize, Alice know the secret. Alice select a random value r. It sends r squared to Bob. Then Bob choose equal to 1. Then Alice compute this one, r into s, and send it to Bob. Then what Bob will do? Bob will compute this one, because Bob knows these things. These are like x. Bob knows x. Okay. Bob knows the v. So v actually contain the square of the secret. Okay, so this value should be equal to the y square. So the y that is sent by Alice. Okay, so these two are same. Then Alice actually authenticate herself to the Bob. But equal to 0, okay, then what will happen? So equal to 0. So in that case, then we will have s to the power 0, right? R into s to the power 0. So s to the power 0 means 1. So R mod n. Okay, so in this case, Alice don't have to know the value of s, right? But also she can verify herself to the Bob, but she doesn't know the s. So it actually, so you can think about, oh, it depends on this value of e, right? So what Trudy can do, Trudy will do this thing. In the first message, Trudy send this x, and whatever the reply from Bob, that doesn't matter. In third message, she sent this one. Okay, so this is true, or through this, Trudy can verify herself if Bob selects 0. If Bob selects 1, it doesn't. Uh, that in that case, Alice doesn't know the s, so she cannot verify herself. Okay, so in this case, she doesn't know the s. So it doesn't need to know the s, because in the equation we don't have the s here, right? So without knowing s, Alice can verify herself. So that's the problem. Okay. So this is the summary. Okay. Because these two values are public. Say everybody knows it. Alice knows s. Okay. So initially, Alice sent x equal to r square mod n to Bob. So she cannot change the value of r later. Okay. So this is like a commitment. Then Bob sent a challenge, the value of e, it can be 0 or 1. So Alice respond with this one, this equation. So if Bob choose 1, then it will be s here. If Bob choose 0, then this should be 1. Okay. Then what Bob will do? Bob will compute this one and check if this equation fulfilled. Then uh, Bob can authenticate like this is Alice. Okay. So does this prove responses from Alice? So that's the issue now. Okay. In mathematically, you can see, okay, this is possible. Let's see. So if everyone followed the protocol, so we have now Alice, we have Bob, and we have Trudy. So everybody is following the protocol. Okay. So now the thing is, instead of Alice, can Trudy convince Bob that she is Alice? Okay. So if Trudy think, or Trudy expect that E equal to 0, okay, E equal to 0. So in that case, what Trudy need to do? She will send at first r square mod n. Okay. So the second message doesn't matter, and in the third message she will send just r. Okay. But if Trudy expect E equal to 1, in that case, because she don't know the value of s, what she can do? So in the first message, in initial message, she will send this value, the square of random value with the inverse of v. Okay, because v is already public, so inverse of v in the message 1, so that in the message 3 she just need to send the value of r. Okay. So if Bob choose anything from 0 to 1 randomly, so Trudy can only trick Bob with probability of half. So here, as I said, that Trudy can trick Bob with probability of half, but after like n iteration, as you see in the Bob's cave, that example, Trudy can convince Bob that she is Alice with 1 by 2 to the power n times. Okay. So the selection of 0 and 1, this must be unpredictable. Okay, so that Trudy cannot predict these two values, and Alice must use the new value, new each iteration. Okay, or if she just choose the same value of r, like she becomes lazy and she just send the same r. So what will happen if equal to 0, if Bob's is select 0, then Alice send the value of r in message 3, and if equal to 1, then Alice sends r into s to the message. Okay, so if it's in the, it is repeated in the same time, I mean couple of time, so then Trudy, what Trudy will do, Trudy will do the same thing. Okay, because the value of r is always same. So she knows the r, she knows the r and s, so Trudy can easily find the value of s, right? So this r should be uh, in every iteration, or every in every iteration the value of r should be changed. So in zero knowledge means that nobody learns anything from the secret, like, because in public we have this part. Okay, and Trudy sees the r square, so Trudy don't have any idea what is r, and also Trudy can see r into s. Okay, if the e is 1, then she can see the r into s. Okay, so if Trudy can find the value of r from r square, okay, so she can easily find the value of s. But the thing is, it requires modular square root. Okay, so it is very difficult to find this modular square root. Okay, so if Trudy could find modular square root, then she can just find it from here, this part, just square root this one. Okay, so the square and the root is cancelled, so she can get the value of s. But the main thing is here, the modular square root, finding modular square root is difficult. Okay. So through this protocol, it doesn't help to find the value of s. Okay, so you cannot find the value of s from the, if you send message using this protocol. So there are some real world implementation of this zero knowledge proof. Okay, uh, in public keys, to identify users who use zero knowledge proof. Okay, like what happened, like if you want to authenticate yourself in a network, what actually we do, we send our certificate. So whenever you send the certificate, that means, so suppose, okay, suppose I am communicating with a server. Okay, so in the middle Trudy is there. Okay, so if I use JKP protocol, zero knowledge proof, so what will happen, Trudy can see the uh, messages, but she actually don't know what are those things. So whenever you send a certificate for authentication, in that time Trudy get to know that, okay, this is the certificate of Alice. Okay, so it actually reveal the information. So there is a NSCRAB, Microsoft Next Generation Secure Computing Base. Okay, this actually support this zero knowledge proof. And also it is used to authenticate software without relieving the machine identifying the data, machine identifying data. Okay, so I think this is the okay, the last one. So if we just summarize, like we have seen lots of protocol, like public key, private key, lots of protocols. So what is the best authentication protocol? So there is no particular answer, because it depends on many things, like uh, the delay of tolerance, Okay, we have seen about time skew, clock skew. Also, the sensibility of the application of data, cost, what kind of cryptographic it is hashed, symmetric or public. Okay, so depending on all these things, actually, we need to select authentication protocol. So there is no such best protocol. Okay, so it will be like I just tell anybody like, okay, give me this protocol. Okay. It's not like that. You have to consider different things and you have to select that. So this is the end of this.